Modern institutions generate thousands of files every day. Research data, thesis drafts, high-resolution scans, and multimedia recordings quickly dissolve into a massive, chaotic archive. Tossing these files onto a shared server does not solve the administrative problem. To be useful, an institutional archive requires these assets to remain searchable, open access, and completely immune to the eventual obsolescence of the software that created them. To meet these strict requirements, libraries and research centers rely heavily on open-source software rather than proprietary vendor systems. This chart showing a software platform's overview highlights the current market reality. DSpace strictly dominates this open-source ecosystem, holding a 40% share of the deployment landscape. Unlike a standard website content management system or an unorganized network drive, DSpace is engineered specifically for deep archiving. Its market dominance stems directly from its internal architecture. The software operates on a rigid, nested information model. For any system archivist or library information science professional, mastering this specific hierarchy of data is the primary requirement for managing a digital repository. By strictly separating the raw file data from the descriptive tags that explain what the file is, this internal structure prevents the long-term digital decay of the archive. The absolute lowest base unit of the DSpace architecture is the bitstream. It acts purely as a format-agnostic container, absorbing formats ranging from text documents to audio files, storing them as raw data. Archivists follow a strict rule. Bitstreams should rely on open, non-proprietary standards. A proprietary file type often requires a specific licensed program. Decades later, when that software ceases to exist, the raw file becomes completely unreadable. To organize these functional base units, DSpace wraps them into the next architectural layer, the bundle. A bundle groups related files together. A single research paper might include the original document alongside supplementary datasets. It automatically stores system-generated files, like an image thumbnail, the plain text extracted for indexing, and the legal usage license. While this neatly groups the raw data, the bundle remains invisible to search engines. It lacks any descriptive context about the information it holds. To make files discoverable, the bundle is encapsulated within an item wrapper, the fundamental digital document of the repository. DSpace enforces a strict structural rule. The item acts as the single exclusive access point. Search queries cannot bypass it to read the bundle directly. The raw bitstreams sitting at the bottom of this stack carry no inherent descriptive data of their own. Instead, the system uses the Dublin Core standard to create a separate metadata package. This package docks to the exterior of the item wrapper. This metadata provides the descriptive details, the author, the subject, the format, and rights-based provenance, allowing the item to be properly categorized. The item then receives a second crucial attachment, a persistent identifier, typically a CNRI handle. Even if the physical server changes or the institution overhauls its web domains, this identifier ensures the item resolves to a permanent functioning link. Notice the physical separation here. The raw files inside never touch the descriptive metadata attached to the outside. Because the metadata is isolated on the item wrapper, external networks using OAI PMAH protocols can harvest the repository's descriptive records without downloading the actual files. When we zoom out to look at thousands of these items, we need a way for human users to navigate them. This brings us to collections. These are organizational buckets grouped by document type or specific user expectations. An archive might group master's theses into one bucket, raw statistical data sets into another, and technical lab reports into a third. Occasionally, a single research paper fits perfectly into two different categories. Rather than copying files and wasting space, DSpace allows a single item to be mapped to multiple collections simultaneously. Finally, collections are grouped into communities at the top hierarchy. A community mirrors the physical and administrative structure of the institution, like top-level blocks for the School of Natural Sciences or medical research. These can be divided further into subcommunities. A humanities block, for example, can split into granular divisions for philosophy, history, and psychology. This upper macrostructure translates an abstract database of files into an intuitive, navigable map of the institution's intellectual output. From the raw bitstream up to the overarching community, the information model is complete. But this elegant structure remains entirely inert without a crucial human element, the system administrator. The administrator determines exactly who is allowed to submit a file, who reviews that submission, and who holds the authorization to edit the metadata. The administrator applies these rules directly to the top tiers, defining custom workflows for individual communities and collections. Supporting both the human workflow and the information model requires a highly specific set of back-end technologies. The repository runs on a strictly open-source technology stack, relying heavily on a Java environment, an Apache Tomcat server, and a Postgres relational database. Running on this specific bedrock allows the software to natively support Unicode character encoding and OAI PMH harvesting protocols. A digital library is not defined by its storage capacity. By wrapping raw files in a rigid, standard-compliant ontology, an institution guarantees its legacy survives long after its current hardware is replaced.